Smart grids observability using Bilevel program.
Thank you, Andy. So I would like to take the chance to thank the organizers for the invitation. It was a very nice experience to visit in February and this week. So today, as Andy said, I'm going to talk about smart grid observability. So the first day, Janusz spoke about PMUs. It will be about installing PMUs on grids to make what I would call the grid smart. Okay, so then everybody that Janusz said about the PMUs will be like valid for this talk, but I'm really looking at the first step. So like, how do we install optimally the PMUs on a grid? So this is a joint work with Pierre-Louis Poirion, who was at the time a postdoc in my group and now is at the Riken Research Center in Tokyo. Sonia Toubaline, who was also a postdoc at the time, and now she's assistant professor at Paris Dauphine, and a colleague from Polytechnique Leo Liberti, CNRS and Polytechnique Leo Liberti. Okay, so first let's talk about smart grids. Of course, probably I'm like the introduction would be like straightforward to all of you, let's say, but I will give you my definition of smart grids, because from time to time, I mean, there are several definitions, let's say, of smart grids. So I'm going to talk about smart grids when I mean that in the grid, in the electrical grid, there are some information technology, added, integrated, okay? So we have a grid, we have some devices installed in the grid that can communicate in particular the status of the grid, okay? This is what I will mean with the term smart grid. So why? So Janusz already spoke about this the first day, so there are several motivations. I will focus on the fact that the grid it will be observable thanks to this, meaning that we can at any time check what is the status of the grid. So it will be helpful when there are, I don't know, shutdowns of some parts of the grid, or to optimize energy efficiency, etc. And then how? So as I said, there will be some devices installed in the grid which will have the capability to communicate the information about the grid. And when? So it's happening now. So actually, I mean, this project was started because of this research project started because of an industrial project with some collaborators, and the aim is to make the grid in France completely smart in 2030. So, okay, so as I said, our focus will be full observability. So we want to guarantee that at any time, so we have enough PMUs on the grid in order to know the status of the network. Oh, sorry, I didn't tell you that if you want to like ask questions during the talk, feel free, because maybe, I mean, some concepts are not straightforward for some of the audience. So as I said, this research was motivated by a project that was a project between two academic partners called Polytechnique and Grenoble in France, and then there were a bunch of industrial partners, among which RDF, ST Microelectronics, etc. And it was like a 4 years project that ended in 2015 and was sponsored by the ADEME, the Agence de l'Environnement et de la Maîtrise de l'Énergie. So it's a public agency for environment who sponsored this research. And right after the project, and for a year, there was like a demonstrator in France, in Toulouse, where smart meters were installed, and also together with some devices, connected devices like PMUs, etc. So thanks to the research that we have done in this area. Okay, yes, as I said, the aim will be to install PMUs in the whole France from here, like until 2030. Okay, so what is the idea? So the idea is that we have a grid. I think that it will be like straightforward to almost everybody. And then we focus on some measurement devices, these PMUs, and then there will be also installed some data concentrator, repeater, smart meters in order to make this grid smart. So as a mathematician, what we did was to speak to our industrial partners and try to formalize from a mathematical viewpoint the problem that they wanted us to solve. So that's what I will do now. So we suppose that we are given a network, a graph actually, G, that is composed of vertices, capital V, and edges, capital E. And then, as I said, the aim of our work was to install the minimum number of PMUs in the network, because we suppose that these PMUs are expensive. And we want to guarantee this full observability of the grid. So meaning that we want at any time to be able to know the voltage at each node of the network, of the grid, and the current at each edge of the grid. So the idea is that our, another constraint is that our PMUs are installed on a node, but they are capable of observing just the voltage at that node and one of the currents at the edges of the node. So just capacity 1. Okay, so this is important because what we will do is to suppose that actually the PMUs are installed on an edge, because they can just like observe that edge. Okay, so from a mathematical viewpoint, this is the assumption that we did. Okay, so this is what our aim is to guarantee that for any V in so the set of nodes, the voltage is known.
Do you also guarantee observability of the topology?
So what do you mean with the observability?
The line is out.
Okay, so I will go at the end. I will actually tell about the robustness. So we have a robust version in which we suppose that we can observe even if we get out. So one line is off.
When the line is out.
Not necessary. So what I will show you is that we can observe anyhow the grid, even if one line is out. Okay. Okay, so from a formal viewpoint, then I define n being the cardinal, so the number of nodes that we have, and m the number of edges that we have in the grid. And then gamma v will be the neighbors of, so the nodes that are linked to v with an edge. Okay. And then we will have pi, that will be the subset of the edges on which we decide where to place the PMUs. Okay, and omega will be the subset of the nodes that are observed. Okay. So the interesting thing of this problem is that we do not, so we use some physical laws in order to guarantee that the nodes are observed even if there is no PMU on that node. Okay, so because otherwise, of course, you will say, I need a PMU for any node. But this is not what we are doing. So we define two propagation rules, meaning that if we observe, so rule number 1 will be using Ohm's law. Rule number 2 will be using Kirchoff law and Ohm's law. So let's go to rule number 1. So suppose we have an edge UV that has a PMU installed. Okay, then we can say that U and V are observed. So it's very simple. So we use this equation in which we know, for example, so we represent here the fact that the PMU is on the edge but closer to U, meaning that it will observe the current of U and the voltage of U and the current on UV. But thanks to the Ohm's law, we can also reconstruct the voltage of the other node of the edge. Okay? Clear so far? Okay. So it means that if we have a PMU here, we know the voltage at the node and we know the current at the edge, and then we can compute the voltage at the other node. Okay. Propagation rule number 2 is a little bit harder. So suppose that we have a vertex here, this one, this B, that is observed. So it's in the set of like omega. And then all its neighbors besides one, that is u in this case, are observed. Okay? So we know that we know also the current on these 3 edges. So we know the current in all the edges besides one. So thanks to Kirchoff's law, we can calculate the current of the last edge. And then, thanks to Ohm's law, we can also observe the last node. Okay? Questions? Okay. So now that we have these 2 rules, we can see, for example, in this very simple example, that if we install the PMUs here and here, then we will observe these 4 nodes thanks to rule number 1. And then we will observe this thanks to rule number 2, because we have this node that has all the neighbors besides one that are observed. Okay? And then we propagate again, and we can show that in order to observe these 6 nodes, we need just 2 PMUs. Okay? Okay, now some background about like literature, like before. So when we started working on this problem, so we formalized this in this way, and then we have seen that it's the node version of a well-known problem that is called power dominating set problem. It was studied from both complexity viewpoint. It was shown to be amply complete for several kinds of graphs. You can see it here, and polynomial for trees and square grids. Then there were also some results on the approximation guarantee that can be like be performed on this, and there were some like methodological papers in which they use integer programming or heuristics in order to solve the problem. But our contribution in this part is that we showed that this problem is NP hard thanks to a reduction to the mean vertex cover. And in particular, we showed also that it's NP hard to approximate it with a factor of this kind. Okay. Actually, this is not the focus of this talk, but I will just mention some results. But it's interesting to see that for some grids that are trees or grids, it's polynomial, and you can see some details in this paper. So what I'll be talking about in this talk is 3 methodological, 3 methods to solve this problem. So the first is what I call the natural mixed integer programming formulation. The second is a mixed integer programming formulation coming from like a bilevel programming. I will talk about this later. And the third is a tailored method for this problem. Okay. Now let's go to the first mathematical programming formulation. So I will call it iteration index formulation, and it's based on the fact that we have a propagation of the observability that can be done iteration after iteration. So the variables are, so we have 3 sets of variables. So the first is Sij for each ij in the edge set, in which that is equal to 1 if the PMU is installed in that edge, on that edge, and 0 otherwise. Then the second one is omega it, that says for each vertex I and iteration t, says if at iteration t the node I was observed. Okay. And then the third one is more complicated, so it's for each edge ij and iteration from 0 to t minus 1. We have yijt equals to 1 if rule number 2 was used at iteration t to observe node node j. Okay, so this is just like a kind of modeling issues. So this is how the iteration index formulation looks like. So we have the minimization of the sum over the Sij. That is the number, basically we want to minimize the number of PMUs that are installed. So this is just a matter of formulation, meaning that we have both Sij, Sji, and then we just say that if a PMU is installed in Ij, it's also installed in Ji. And then our aim is that at the last iteration, all the nodes are observed. Okay? And then this is about the starting point, so meaning that if a PMU is installed on an edge of vertex I, then the corresponding variable omega I 0 can be greater than 0. Otherwise, no. For iteration 0. So at iteration 0, the only nodes that will be observed will be the ones that are part of an edge where a PMU is installed. And then these three constraints, I won't give you details, but they actually model the fact that the rule number 2, basically. It's pretty simple. And the last thing here, besides the fact that they are all binary variables, we have that if a node I is observed at iteration t, then it will be observed also in the next iterations. Okay? Questions? So there are two things. So one observation is that we need to give a value to capital T. Yes?
The time horizon.
Yeah, exactly. So the T, capital T, we need to give a value to that. And actually we could prove that the worst case, so the number of iterations that you mean at maximum is equivalent to n minus 2. So the number of nodes minus 2. Because at iteration, because you need at least one PMU in order to observe something. And at iteration 0, if you have one PMU, you will observe 2 nodes. And so you will need maximum like n minus 2 iterations in order to propagate the observability. And then the second thing is that, of course, if you look at these, I mean, these values can be very high, so we can have a lot of binary variables, and actually I will show you later that this model was easy to solve only for very tiny problems, of course. So that's why we were motivated to find other methods. The next method is bilevel programming formulation. So we have a very, so the observation that we had was that we have a characteristic vector of the observed nodes, that is omega, that can be either 1 if the node is observed or 0 otherwise. Okay, so this is the definition of omega. So here we are not considering the iteration. So suppose that we have a function theta that takes as input a vector of size n of binaries, and the output is a vector of size n of binaries. And actually we define theta I of x as this thing. So what's the meaning? The meaning is that, so the input will be the current situation of observability at iteration t, let's say. And so here we have the maximum between these. So meaning that if this is 1, then the value will keep being 1. And this other function will be equal to 1, so greater or equal to 1, actually equal to 1, only if rule number 2 applies. Okay, so we look at any of the neighbors of I, and we have that 1 minus the cardinality of its neighbors, of neighbors of J, plus the fact that the node J is observed or not, plus the fact that all the neighbors but I is observed or not, will give us 1 only if j is observed and all the neighbors of j are observed besides I. Okay, so in this case, we will have that this and these three terms will be equal to 0, will sum up to 0, and then we will have 1 here. Otherwise, it will be, so this term will be smaller than 1. So, in practice, the meaning is that this theta, so if we give to theta as an input the vector of the current observability of the nodes, then it will try to apply rule number 1 to propagate the observability. So actually what we want to find, so this is the idea, so like suppose that we have omega t, so at iteration t, and then theta omega t will give us the omega t plus 1. And actually what we aim for is the fixed point, a fixed point of this function. And we could prove that what we want to find as observability, to satisfy the observability propagation, is the smallest fixed point of theta. Okay. So this all to bring to a new formulation that doesn't contain the iterations and actually looks like this. We have omega without an iteration index, so omega is just concerned just the node, and this will be greater or equal than Sij. So if PMU is installed in Ij, then omega I will be 1. Then this is the constraints that comes from the definition of this, so that like model rule number 2. And then in order to get a small fixed point of this function here, we have to minimize the sum of the omegas. And if we look at the whole problem, so it will look like this. So suppose that we have, the constraint that we have in the objective function that we have before. So in the upper, in what we call the upper level, so this part here, we will have the decision on where to place the PMUs. And we want to minimize the number of PMUs installed. And then we have this optimization problem inside the optimization problem. This is what the definition of bilevel programming formulation. So bilevel means that there is an optimization problem inside the optimization problem. And the minimum value of this optimization problem has to be greater or equal than n. So the value of the fixed point of this function here has to be n. So this will guarantee that the observed nodes have all the nodes of the grid. Questions? Okay, now the question is how to solve this problem, because the solvers that we have at N typically do not solve this problem. So we propose two methods. One is to transform this into a single MILP, and I will show you immediately how to do it. And the other one is to design a tailored algorithm. Okay, then, so how do we get a single level problem? So a classical way of solving bilevel programming is to reformulate this. So there are two ways basically. One is to get the KKT conditions, the optimality conditions of the second problem, of the inner problem. And the other is to make this, transform this as its dual and to get a single level problem. So this is what we will do. But the first observation is that we can relax the lower level problem to because omega I were binary variables, and we can relax them as a continuous variable, like non-negative. And this is because we could prove that for any fractional optimal solution of this, there exists an integer solution of this. Now, what we can do is to make the dual of the inner problem, of the lower level problem, and then we know that thanks to the properties of this class of bilevel problems, we can relax this so as to get rid of the max. So we can say that we want this constraint to be valid to any of the solutions of this subproblem. So this becomes a constraint like this that doesn't contain anymore the maximum, so it's not an optimization problem anymore, but it has a product of variables. And the next step is to linearize the product of the variable. That can be done because one of the two variables, Sij, is binary. So this is the final model that we have. Okay, so that has binary variable S that were there before, and then these other variables that comes from the dual of the inner problem. But it is a problem that we can solve with, for example, Cplex. Now, so we tested this, and it this method was working better than the previous one, but we wanted to improve even further. So what we do is to devise a cut-in plane algorithm that looks like this. So we are given a subproblem pk that is a relaxation of our original problem, and in particular we will consider only the constraints corresponding to the upper level problem plus some cuts that will be added iteration after iteration, and I will show you now how to obtain this cut. Actually, the main framework looks like this. We start and we iterate until termination condition is not met, and we solve this problem here that at the beginning will be just contain the upper level problem. And then iteration after iteration, we will call a procedure that is called generate cut, that will, first of all, check if the solution S of this subproblem is feasible for the original problem. And then if it's not, it will generate a cut in order to cut the solution. And this is the update of the problem. Now, how to get the valid inequalities for this? So the physical interpretation is that if we do not have, let's say the constraints are not satisfied, so if the only constraint that we have is that all vertices are observed. If this is not the case, that it means that we do not have enough PMUs in the grid. So it's a straightforward thing. So the idea is to add some PMUs, and of course the only places where we can add them is where in the edges where there is not already a PMU. Okay, so this is actually a very simple consideration. And then iteration after iteration, so iteration after iteration, here we will get S that will be will correspond to a number of observed nodes that is typically smaller than V until we get to the last iteration in which we came with the PMU installation that correspond to complete observability. So it means that the first k vectors are infeasible for the upper level, and then we can separate them through a cut that can be obtained like this. So the alphas will be just the logical complement of the current solution. So meaning that we want to be able to, we want to say that there will be at least one edge where there is not already a PMU, where we have to install a PMU. It's really from a physical viewpoint, it's really straightforward, and probably it's not the best that you can do, and in fact I will show you how to strengthen this. So of course, if the current solution is infeasible, then this cut will violate the will actually remove this solution from the set of solutions. And actually, in order to make the cut stronger, we can also make another observation that is about the fact that, so suppose that we have like some observed node by this given PMU installation. Then we are saying that we want to install an edge in one of the a PMU in one of the edges that is not doesn't contain a PMU anymore. But if you think about the rules, actually installing a PMU where on an edge that already has the two extremes that are observed won't change anything. Okay, so we can strengthen, so we can have a better cut by saying that we want to basically, well, the observation is like this. So we want to add the PMUs on an edge only if so it's useless, as I said, to say like to add the PMUs on IJ if IJ are both already observed, because it won't change anything. And so what we will do is to devise a cut like this one, where the alphas are equal to 1 only if either I or J is not observed. Now the generation cut procedure looks like this. So we solve the lower level, so we get an S as an input, and we solve the sub-problem concerning the observability, and we get the observation, the observed nodes. If this the sum of the observed nodes is equal to n, then we are done. So we found a solution. Otherwise, we generate a cut, and actually the alphas of this cut will be equal to 1 only if if one of the two nodes ij is not observed, 0 otherwise. So in practice, so we start, for example, with a simple PMU placement like here. We observe 1 and 2 thanks to rule number 1, and 3 and 6 thanks to rule number 2. But then we cannot observe 4 and 5. So what do? We will add a PMU here, for example, and we can reach all the other nodes. But actually the cut that was added was, so first of all, let's say that these edges, this one, and this one, have both nodes that are observed, so there is no need to add a PMU on this. So the cut will tell us to add a PMU on one of these red edges. Okay? So this is the cut that we'll generate. We say, so either add the PMU at S24 or 25 or 34 or 35. Not in the others, because there is no need. So, and then starting from this, we were able to also further generalize the methods to a more general class of bilevel programming that looks like this. So we have a minimization of a linear function of variables of the upper level, subject to some constraints, and these are binary variables. And then we have a constraint on the objective function value of the lower level problem. But I won't explain this. So just to say a few words, of course, as this method was like more general, it was even less efficient. So it will be a row and cut generator algorithm, and then it's less efficient unless you do some assumptions. Now, computational results. So this is the server that we use to test the problem, and we developed everything on the Julia environment thanks to the JUMP language, that is Julia for mathematical programming, and the solver used to solve the MILP problems was Cplex version 12.6. We got a time limit of 2 hours, and we tested the problem on 2 kind of instances. The first was taken from IEEE and bus systems with number of nodes from 5 to 118. And then the second part was the second set is random graphs with n nodes and 1.4 times n edges. 1.4 was the average of the edges of the IEEE grids. And we consider n from 5 to 10. And for each value of n, we consider 10 different instances. We generate 10 different instances. What we will see is the average performance on these 10 instances. So, the table of results. So you can see here that this block concerns the IEEE instances, and this other block concerns the random instances. And you have in the column here number of nodes, and here number of edges. And for each of the next 3 blocks, you have, so for this is correspond to the first model, so the iteration-based model. This is the MILP obtained by making the dual of the bilevel program, and this is the cut-in plane. For each of these blocks, you have time limit, percentage gap, so how far is we are to prove optimality of the solution, and then the number of instances that were solved to optimality. So you can see that the first model I showed you can be solved up to like 14 nodes, 15 nodes, and then it becomes completely unpracticable. Because already from 20, every time it's the time limit of 2 hours. So it was way too difficult to solve. And then the second method is the MILP coming from the bilevel, performs a little bit better because we can go up to 30 for the first case and up to, let's say, 25, because here we solve all the instances, and then at 30 here it starts getting troubles into finding the best solution. And the cut-in plane, on the contrary, can solve almost all the instances besides one of size 50. So we got like an interesting improvement for this viewpoint. Now, so to conclude, so we have proposed 2 mathematical programming formulations. The first one was iteration-based formulation, and the second is a bilevel, for which we proposed on one side to solve it as a single level problem, and on the other side to a cut-in plane algorithm that it was tailored for this specific problem. We also generalized this to a class of bilevel problems, and what I didn't show was the what I was mentioning before, so the robust extension. So we could prove in the paper that we can easily extend the methods that I showed here to the case in which you want to guarantee full observability of the network, also in the case of single line outage contingency. Okay, so we suppose that you have an edge that is off, and then you cannot propagate through that edge, the observability. So we can also use an extension of this method to take care, so to compute where to install the PMUs to be robust also to this failure. And then the second thing is about measure losses. So suppose that you have a PMU that won't work anymore, and it will not give you observability of one node. Then we can also, in this case, extend this method that I showed to the case in which even if we lose one of the PMUs, any of the PMUs, then we still can compute full observability of the grid. Okay, now current and future work. So on one side, from a theoretical viewpoint, we are further generalizing the algorithm to the case of convex functions, etc. And on the other side, that is more interesting from a practical viewpoint, we are now considering the PMU placement, in which we include a part that comes from the state estimation. So there are some techniques that allow us to estimate the state of part of the grid, and we extended the formulation to the case of PMU placement, in which part of the grid is the state of the grid is estimated but we guarantee a given error. Okay, and in this case we have a tri-level formulation. It's very difficult to solve, but actually it's a ongoing work with the next speaker and some other colleagues that are mentioned here. And this is the formulation I show you that just to impress you, because I won't give you the details about the formulation. So actually this is very, I mean, this is the first, what we had before. Also this is pretty similar. And then we have an extra optimization problem here that is inside the second optimization problem. So we hope to have results soon. Claudia, so the student of Claudia who's very good is working on a method to solve this problem. And with this, I thank you for your attention.
Do we have time for questions? Yes?
So a power system would be probably a planar graph. So is that something you are able to exploit?
Yes, I think so. Planar graphs, I would say that I mean, if you have a structure of the grid in general, you can exploit it. I wouldn't say that it becomes easy to solve, but if you have a given structure, there are ways to improve the method. Yeah.
Just as an idea, in those problems that you could solve to optimality, were there multiple optimal solutions? And what was the ratio between the number of lines and the number of PMUs in the end?
Okay, so this is an interesting question. So yes, there were several equivalent solutions, and actually the number of PMUs was very limited with respect to the number of edges. So there were, I mean, the structure of the grid, it really depends on how your grid looks like. So if it's really, if it's very dense or not, and how so basically how it is built. But I would say that, for example, if it's kind of sparse, it will be easier to observe it. So suppose, for example, that you have just like one line of like edges, then you just need a PMU to observe everything. So you know what I mean? Yes. So probably, I mean, maybe we should have also tested on denser instances, because we didn't really make a sensitivity analysis on the density of the graph, because what we did was to take the average of the density of this graph and also use it for the random networks. But I would say in general that would be like easier for the sparse graph than for the dense graph to find the solution.
But if you have a, let's say, tree-like graph, okay, you can propagate, of course, the currents, but then you have at each node some loads that may disappear, which you probably should have to measure as well to make this work, right?
Yes. Yes, actually, anytime you branch, basically you have to add a PMU, kind of.
Unless you know an impedance for that load.
Yeah.
Since you don't know the impedance, you have to.
Yeah, sure, yeah. But I mean, by experience, actually, what we have seen as the number of PMUs needed to be installed, it was very low number, and actually the practitioners were surprised by this result.
Thank you very much for your presentation.
Thank you.
How important is the accuracy of the power system model to propagate the measurements of the PMU?
Yeah, so
the real experience you have.
Yeah, actually, the real I think that we will know better, when we will get to like solve the state estimation version. Yeah, I would say that if you have something wrong, probably it would be useful to have this robust version in which you can get out one measure and then rebuild it anyhow. So I would say that probably what you will need to do is to so suppose that you can say, so bound the number of measurements that are not accurate, then you can probably write a robust version in which even if you do not consider some of the measures, then you can find the proper estimate, so observability. Does it answer to that? Yeah, okay. Yeah.
So, this may not be a very well-formed question, so bear with me while I'm sort of forming it on. From my understanding, whenever they're placing PMUs in India right now, and they're doing a lot of aggressive PMU installation, they want to place PMUs at both ends. So if they pick an edge, they want to put PMUs at both terminal ends. This is because of the nature of the line and so on and so forth. It also helps in doing other analytics that you could do with PMUs from a protection perspective, from a line parameter estimation perspective, and a whole bunch of other analytics. And I don't work in this area, so I cannot comment very more concretely on this, but I've seen work on these lines where you could leverage the fact that you have PMUs on both ends to better protect the system and to better do other analytics with the system. Can you comment a little bit on how this would complicate your analysis if you were to basically say, whenever I place a PMU on an edge, I'm basically placing PMUs on two ends and not just one end necessarily?
Two ends, okay, let me think. Well, I think that probably you are going to have like further constraints on the, sorry, I will go back to the bilevel. Okay, so probably you just need to have an extra constraint in the upper level that says that if so if one Sij becomes 1, then another one has to become 1, if I got it right. So you have just to, I mean, if you have offline the correspondence between the edges that are at endpoints, let's say, I would say that probably the generalization is straightforward.
No, I was just thinking, do you have an intuition in terms of, so for example,
if it makes things easier,
and it said that you need to pick n edges. Now, if you were to add that one extra constraint in, I don't think you would bring the n down by 2, but would you bring it down, or would it remain the same, or would it? Do you have any intuition on that, or it's okay if you don't have?
No, probably I don't have. But I would say that having more constraints will limit the space of research, of search that you will do. So in theory, it will ease things. So meaning that the space that you have to like explore will be smaller. So probably it will be easier. But then you never know.
I have a question. This is for an AC system, right? Not for a DC system.
I mean, it's in general, yes, yeah.
If you're doing it for a DC system, I mean, you would get linear equations that specify how the currents and voltages work, right? So, is there work that's related to this that tries to seek how many variables you need to know in a system of equations?
Yeah. It's linked to that. Yeah. Interesting.
And do they have similar results to?
I do not know actually. Yes, if someone working on this, but it's an interesting remark. Thank you.
Okay, there's no further questions. Thank you, Claudia.
Thank you.